Hey, I'm Rachel,
And I'm Marissa.
and welcome to ChemisTEA. By the way, Marissa, I like your outfit today. Is that what people are wearing these days?
Yeah, this is the trend nowadays.
You know what? I always have a hard time keeping up with the trends. It just changes so quickly.
Yeah, that's true, but you know what are some trends that never really change?
The trends of the periodic table.
First, we have atomic size, or atomic radii, and it's half the distance between the two nuclei of the two atoms of the same element. This trend decreases across a period, and that's because as you move from left to right, the effective nuclear charge increases. The increase in nuclear charge occurs because as you move across the period, the number of protons and electrons increase by the same amount. However, since the electrons are in the same shell, additional shielding does not occur. This is significant because it means that the Coulombic attraction between the nucleus and its electrons is stronger, so the atomic radii decreases. Atomic radii also increases going down a group. As you go down a group, the number of energy levels increases. The increased distance between the nucleus and the outermost energy level results in a greater atomic radii. This is analogous to a tree's rings. More rings meaning a bigger radius. So most of the group 1A alkali metals would have the largest atomic radius, whereas group 8A, the noble gases, would have the smallest. However, this trend is not very straightforward with transition metals, since in some elements like chromium and copper, some shells are not filled in order to fill others, resulting in increased electron shielding and a greater radius. So, when comparing the atomic size of two elements, remember this general trend of decreasing from left to right and increasing from top to bottom. But don't forget that some transition metals are unique and don't follow this trend. Another important fact to consider when thinking about atomic radii is the Heisenberg uncertainty principle, which states that there is a limit to what can be known about a particle. It is difficult to know an electron's exact position, so atomic radii is hard to calculate and not fixed.
Ionization energy is the energy needed to remove the highest energy electron of an isolated atom in its gaseous state. Here, we're just going to discuss the first ionization energies, which essentially measures how difficult it is to remove one electron from the atom. Ionization energy generally increases across a period and decreases down a group. This is primarily due to the atomic radii, which generally decreases as you move across. So, with the shorter distance between the electron and the nucleus, there is a greater attraction between the opposite charges of the electrons and protons. Then ionization energy decreases as you go down a group because atomic radii increases due to the greater number of electron shells. The greater the distance the valence electrons has from the nucleus, the weaker the hold that the nucleus has on its valence electrons. Coulomb's law states that the greater the magnitude, the greater the electric force. The Coulombic force supports that the greater amount of protons as we go across the periodic table means that the nucleus would have a tighter hold on its electrons. However, there are some exceptions to this trend, as you can see between group 2 and group 3A, and then between group 5A and 6A. For group 2 and 3A, we can see this with beryllium and boron, as the electrons in boron exist in the 2p sublevel and should be shielded by the electrons in the 2s level. The outer electrons are partially shielded from attraction of the protons in the nucleus by inner electrons, and therefore easier to remove than those of beryllium. For group 5A and 6A, we can see this in nitrogen and oxygen. The electron in oxygen in the 2p sublevel is already paired with another electron, while nitrogen has only single electrons in each of its 2p orbitals. Therefore, the energy needed to remove that first electron would be less for oxygen due to electron repulsion of the pair in that orbital. So you can see that the patterns of ionization energy is opposite of the trends of atomic radii.
Electron affinity is the measurement of energy change that occurs when an electron is added to a neutral atom. Generally, electron affinity increases or becomes more negative as you move across the periodic table. This is because as you move across a period, attraction between the nucleus and its electrons increases, meaning that more energy will be released when an electron is added. Another reason for this trend is valence electrons. These increase as you go across the period. An atom with more valence electrons is generally more likely to accept an electron in order to complete its octet. As you go down a group, electron affinity decreases. This is because the atomic number and the distance between the valence electrons and the nucleus increases. This means that the Coulombic force is less, so less energy is released when an electron is added. Now let's see this trend in action. If you were to look at a graph of the electron affinities of the elements, you would see that the halogens' electron affinities are the greatest. That's because halogens only need one more electron to complete their octet. On the other hand, the alkaline earth metals and noble gases have electron affinities of 0 because they are in a stable configuration with their last orbitals filled. Electron affinities trend is therefore similar to ionization energy.
Electronegativity is the ability of an atom to attract shared electrons to itself within covalently bonded molecules. The atomic radii is also the reason for this trend. Atoms with larger atomic radii have a greater distance between the nucleus of one atom and the valence electrons of its covalently bonded partner atom. Therefore, when we go down the periods, we see that electronegativity would decrease since atomic radii increases. Now, according to Coulomb's law, the greater magnitude of the protons as we go across the period would mean that the nucleus would have a tighter hold on its electrons and would even want to pull the electrons of other atoms. This means that the more protons, the greater the electronegativity. This also factors into how many valence electrons belong to each of the groups. For example, the group 1 alkali metals have one valence electron and would be more willing to give that electron away when sharing to get a full shell. Meanwhile, the group A noble gases would be an exception to having electronegativities because they already have a full shell and wouldn't need to attract shared electrons. That makes them generally unreactive, as they'll be reluctant to share their electrons and have zero electronegativity. So even if you tell them a funny joke, they won't react. Fluorine is the most electronegative element of the periodic table and has 7 valence electrons. So think of it like this. We can say that fluorine is so close to being full but still hungry for more food. Therefore, it would be less willing to share its food with like sodium, which is already full and even ate more. Wow, I forgot how many exceptions there were to these periodic trends. Still, I think I'm more confident in keeping up with these trends than the fashion trends right now.
Too bad our fashion trends aren't as consistent as these.
And that was ChemisTEA.
Keeping up with the trends.